Okay, so we continue our discussion about matrices to solve systems of equations with some kind of weird solutions that we get. So oftentimes when you solve a system of equation, you get a solution, you're happy, and you move on. But other things can occur. So for example, you can get a no solution type situation. So see this matrix up here where we have zeros across the bottom and then our very last term is not zero. So think about how you would interpret that in terms of an equation. If we were to move that back to an equation, it would be this right here. It would be 0x plus 0y plus 0z equals 5, which of course simplifies to 0 equals 5. Well, 0 does not equal 5. So that indicates to us that we are dealing with no solution. So when you see this where you get zeros all the way across on the bottom and then you don't have a 0 here, that indicates that the system that you are trying to solve has no solution. Okay, that one's pretty easy to deal with because then you have no solution. In the scenario, there's another thing that can happen where you get this. So see this matrix, we start with our matrix, we're doing the row operations here, and then you get down to here and you have zeros all the way across. So think about how we would interpret that. That would be 0x plus 0y plus 0z equals 0. In other words, 0 equals 0. Well, that is a true statement. So what has happened here? Well, what this shows us is that one of our original equations was a linear combination of the other equations. So it could have just been a multiple of one of the equations, or it could have been much harder to spot. It could be 2 times the first equation minus 3 times the second equation gives you the third equation. You're probably not going to spot that right away, but when you go to do the simplification using your row operations, it's going to pop out like this on the bottom. So what that means is we now have more variables in our problem than we have equations. We've essentially reduced this to a system that has 2 equations in 3 variables. That's going to leave us with an infinite number of solutions. We call this a dependent system. If your solution has no solution, if your system has no solutions, we call it an inconsistent system. If it is like this, where it has an infinite number of solutions, we call it a dependent system. Okay. And I want to go through this traffic control problem because I think it's a good problem. I think we can kind of wrap up everything we need to know from this section just in this one example. And you'll see a couple homework problems like this. So I want to go through and show you how to do this. So what we have is an intersection. There's 4 intersections here labeled I1, I2, I3, and I4. And you can see what we have is information about incoming or outgoing traffic. We don't have both. We don't know what's going on. So for instance, at I1 here, in fact, let me blow this up a little bit. Okay, so I've zoomed in now. We can see our equation. So intersection 1 has 700 cars an hour coming in from the left, or I guess that would be the west, and 300 cars an hour coming in from the north. Okay, but we don't know what those cars are doing. The cars here coming in from the west could be going straight. They could be turning right. These cars coming from the north could be going straight or turning left in this case, right? These are one-way streets. You can see they're kind of, just for simplicity's sake, you could model stuff with two-way streets, but it would get much more complicated quickly. So we're starting with a simpler example here. So what we know is that 1,000 cars an hour are entering intersection 1. Well, what we know from that is if 1,000 cars an hour are entering intersection 1, then 1,000 cars an hour must be exiting intersection 1, right? Because if 1,000 cars an hour are entering intersection 1 and only 950 cars an hour are leaving intersection 1, then that means 50 cars are left inside the intersection. That means you have a traffic jam. Nothing's happening, right? So we can operate on the assumption our goal is to keep traffic moving. And if our goal is to keep traffic moving, then 1,000 cars entering an intersection in an hour better mean that 1,000 cars are exiting the intersection in an hour, right? And that's the rule we're going to use to construct our system of equations. You're going to go through and you're going to create one equation for each intersection. So basically, 1,000 cars an hour have to be either some of them are going to exit on street W, some of them are going to exit on street Z. So what that means is W plus Z equals 1,000, the total number of cars here. So let's go to intersection 2. It looks like 1,100 cars an hour are exiting intersection 2, Well, if we have maintained a flow of traffic, that must mean that 1,100 cars an hour are entering that intersection. So W plus X would be equal to 1,100. Okay, so for intersection 3, 700 cars an hour are entering intersection 3. That means 700 cars an hour exiting intersection 3. In other words, X plus Y is equal to 700. Over here at intersection 4, 600 cars an hour are exiting intersection 4. That means 600 cars an hour are entering intersection 4. So that's how you build your system of equations for this thing. So we end up with this system of equation. This is how you build that, right? This is what we just walked through, the 4 intersections. These numbers should sound familiar because we just named those. That's our system of equations. We turn this into our augmented matrix right here, and then using our row operations, we end up with this down here. This is our simplified version. Okay. Now, each of these rows we can see represents an equation, and they tell us here how to convert back into those equations. So this would be column W, column X, column Y, and column Z. So in this case, W plus Z equals 1,000, X minus Z equals 100, and Y plus Z equals 600. Okay, but what are we supposed to do with that? How are we supposed to write this system in a way that is helpful? So what you do is you take each of these equations and you solve for the variable, either W, X, or Y. So we would solve this first one for W, we'd solve the second one for X, and we'd solve the third one for Y. Right? So that's what we have here. W equals 1,000 minus Z, X is equal to 100 plus Z, and Y equals 600 minus Z. So what we have is all of those variables in terms of Z. So then we can write our vector. Right, here's our vector. So what you do is you pick a Z value, and once you pick a Z value, it pins down all your other values, right? So here we've got, once you pick Z, the whole solution is defined. So there's an infinite number of solutions, but you have to pick a Z value. Okay, now for our intersection, it doesn't make sense. If we look at our picture, it doesn't make sense that Z would be negative because we're not going to have negative traffic somewhere, right? So Z should be positive, probably going to be an integer, makes the most sense. And it's probably not going to be something crazy like a billion, right? So we can start picking values for Z that make sense and say, okay, well, what if, like in this particular problem, they say, what if we restrict Z to be 50 because there's construction going on there? Well, then you take 50 and you plug it in for Z, and that tells you what the traffic will have to be on the other streets. In other words, if you have traffic on one street, then the streets around that, if you have construction on one street, the streets around it have to be able to pick up some of that extra traffic because people are going to try to go around the construction. So this will tell you if traffic is restricted to 50 cars an hour on Z, what's that going to do to the other streets over here? And then you can see if your city can handle that on those streets. If this is Palm Drive here is a residential neighborhood, it probably can't handle 950 cars an hour. If it's a pretty main street, then maybe it's going to work out okay. Okay, so that's the key. Some people get a little confused with this step right in here, which is taking this augmented matrix and turning it into the proper way to write your infinite solution, which is basically a bunch of vectors. But you just write it. You've got your W value, your X value, your Y value, and your Z value. And as soon as you pick something for Z, all of these are defined, and then you can answer your question. Okay, so that's really all there is to that. Right? And I know it seems kind of complicated at first, but once, I would work through this example in the book with the explanation that I just gave you, and it helps it make a little bit more sense.